which is why the factor of area comes in here. And I think of all of these as little springs which are pulled out in order to extend this little piece of metal. Note that the force that I apply here is always perpendicular in this particular case to the area. That's not how it always needs to be. For example, in general, given some sort of area here, let us say this is some small element of area dA, I can apply and suppose dA has a normal which is n hat here. This situation corresponds to applying the force in the direction of the normal, because the normal is this surface, it's perpendicular to that. But in general, I could choose to apply my force in some arbitrary direction with respect to the normal. Okay. So again, in general, if I imagined a little block here of area, I could break up any arbitrary force here with respect to the normal n hat in terms of a normal component Fn and a component that is tangential to the surface. So let me call it F sub t. So this is just saying that given a little bit of area of whatever it is that I am trying to deform, a little area element, in general my force does not have to be perpendicular to that area element. It could have a component that is perpendicular and a component that is parallel. Okay. So this you might call the normal component to the force, and this you might call the tangential component, where tangential is with respect to the surface and the normal to the surface. And this is also called sometimes the shear component, SHEAR. So what do all these things mean, and how can we put them into somewhat more general description when we think about materials? So right now what we are going to discuss is something called continuum mechanics, or the very basics of continuum mechanics at the level of that you might require it in whatever you want to do in a biophysical context. So when we think about continuum mechanics, we don't worry about the fact that all matter is made up of individual atoms here, but we treat matter itself as a continuum. What we mean by that is that we assign a meaning to quantities like the mass density, so the density at point r times t, and the meaning of this is if I multiply this by some small volume dV, this gives me the number or the mass of the number of particles, or if this is the mass density, this will give me the mass of particles in that region. But my only reference to the fact that nature is atomic in character is only through very indirectly through the fact that I say that on average I can describe this at any point by local density. So I'm going to replace everything wherever I can by densities, by the momentum density. So if I take the momentum density and multiply it by a little volume, that gives me the amount of momentum in a little chunk. Okay? And the reason is that provided I remember that the spacing between atoms typically in a fluid or a solid is of the order of angstroms, which is very small. But if I look at regions that are much larger than that, so for example, even if I look at regions that are of order say 10 nanometers or let's say 100 nanometers, this contains many, many particles. So fluctuations of the density about this, provided it is large enough, become small enough that I can really treat this as a smoothly varying quantity. So the first step of treating things in the continuum is to say that there is a smoothly varying field, such as a density field, with the interpretation that if I ask what is the density at a particular point r at time t, the meaning is that if I multiply this quantity by a little volume, this gives me the number of particles in that region, and it's not 0, 1, but some large number. Okay? So continuum mechanics relies on the fact that we can replace the actual atomic coordinates by densities of various quantities that we want to calculate. So now let us try and understand what it means to deform something. So typically the experiment that I have in mind is an experiment that looks a little bit like this. I take a block, I put it on a surface here, and then let us imagine that I have stuck some quantity, some plate here and this plate is attached to some weight which is pulling downwards. This point is anchored to the particular surface. At time t equal to 0, I let the weight slip. This makes sure that since the weight is coming down, that exerts a force on all of these molecules here and helps to distort this block into some new shape. Okay? The force here is a shear force. It's not a force that is normal because all of these molecules in the top layer are being pushed to the right hand side. I am not taking the block and moving it as a whole because I have fixed this particular point here. So this point is fixed, the top side is moving. So all of the points, say at this level and this level and this level, slowly increase in their separation from this point, from the vertical. Okay. So let's just put in some notation here. Let me call this D. Let me call this H. And the force that this exerts here is F. So if I say that this is a block with some area A, force per unit area, the tangential force per unit area, let me call that sigma. Let me define a quantity, let me call it gamma, which is D divided by H. This quantity is a force per unit area. So the units of sigma are Newton per meter square or dynes per centimeter square or whatever it is. It's a force divided by an area. This quantity here is dimensionless because it's a ratio of two lengths. The names for this are, this is a strain and this, as you will recognize, is a stress. In particular, it's a shear stress because it's tangential to the surface. Okay. So now this is the main distinction between solids and liquids. For solids, if I apply a shear stress here, this block will deform in this way until the energy cost of the deformation is balanced by the energy cost of this thing being pulled down. Okay. So I have gone from a situation which is like this to a situation where my block itself is deformed by a certain amount that is given by the ratio D divided by H, where D by H is gamma, which is my strain. Okay. This statement here is the same as the statement that sigma and gamma are proportional, with the proportionality constant being something called G. Okay. So this is an example of something called an elastic constant, and or it's proportional to an elastic constant, but this quantity y is another type of elastic constant that we wrote down here. Here is the distinction between solids and liquids. As I pulled this force, as I pull this down, I exert a force on this, this material deforms until such point where the restoring force backwards equals the force that is exerted by this wall downward. So this is the standard way of thinking about elastic materials. If I take a spring and squish it, it pushes out. It's unstable. It's stable as long as I'm holding it, but once I release that, it moves out to equilibrium. So similarly, once if I just cut this, then this switches back. So elastic, this is an example of a material called, which is elastic. And elastic solid material is something that snaps back to its initial position once I remove the strain that I am applying, the stress that I am applying to deform it. Interestingly, if I take a liquid and do the same thing, so if I take a liquid between say two plates, I move the top plate relative to the bottom plate, so that now initially it was a box that was like this, now it's a box that is deformed. Now I stop deforming it. Question is, does it snap back here? And the answer is that it doesn't. And this is the main distinction between a solid and a liquid. A solid deforms elastically. I change it, I deform it in some way, it springs back when I release the force that is required to create the deformation. For a liquid on the other hand, if I deform it without, very importantly, changing its volume. So these deformations, the simple one that I showed you here, is an example of a deformation that keeps the volume fixed, but just changes the shape.
So how do we do the experiment on liquid?
So one way it's done is to take, for example, two concentric cylinders, put the liquid in between this, keep the central cylinder fixed and rotate the outer cylinder. So the outer cylinder is moving with some velocity v, the inner cylinder is fixed. So we know that liquids have the following property, that liquids have the value of the velocity of the surface they are closest to. So molecules that are very close to this surface here have the velocity of this surface, which is 0. Whereas molecules close to this surface here have the velocity of this surface, which is v. So there is a gradient in the velocity, it's maximum at this wall, and then it becomes smaller and smaller and smaller as I approach this. Okay? So this is one way of deforming a liquid in this manner. But as I said, the liquid doesn't spring back. So what is the meaning? So what is the meaning that I must assign to an expression like this? This cannot obviously be the right answer, because this says that the energy is minimum if gamma is minimum. It wants to, the moment I set sigma equal to 0, then gamma must be 0, because G is always non-zero. So the way one writes that is to say there is again a quantity called the stress. There is a force per unit area that must be exerted in order to deform it, but that is proportional to, say, let me say eta times not gamma, but the rate at which gamma changes, which is gamma dot. Okay? So what that means in this example is, as I keep rotating my cylinder, I must exert a force constantly to rotate it. The liquid moves around, but the memory of the fact that the liquid does not like to be deformed is in the fact that it obeys a relationship like this. Liquids are sensitive not to deformations, but how fast they happen, to deformation rates. Okay? So this is a deformation rate or a strain rate. This quantity here is called a viscosity, and this here is again the stress. Okay? So now this is the distinction between a solid and a liquid. Solids, when deformed, spring back to their undeformed position when you remove the force. Liquids, when deformed, do not go back. However, the energy that I must apply to deform a liquid is proportional to the rate at which that deformation happens. And the proportionality constant is the viscosity. And the force that I must exert to keep it moving is the stress for the liquid. Okay? So again, liquids resist compression or expansion. Liquids exhibit the property of what is called cohesion. Its molecules like to be together. A gas is not cohesive, but in a liquid there is an advantage to the molecules being close to each other. So they resist both compression and expansion. There is a preferred density to the liquid. However, liquids deform under shear, and the stress is proportional to the strain rate.
Is it solids which stresses?
Both solids and liquids. In this, they are not very different. Solids and liquids resist compression or expansion. They resist volume changes, but while liquids deform under shear, solids swing back. Solids show elastic response. Under shear. Okay? So stress is proportional to strain rate for a liquid, stress is proportional to strain for a solid. And the proportionality constant here is the viscosity. Over here it's an elastic constant. So this really is the difference between a solid and a liquid.
Viscosity will determine how much stress can the liquid take, right?
Hmm.
But for solid, the elastic constant is after deformation, at what rate it can come back.
So for the solid, it just says that the restoring force that wants to push it back is proportional to the how much you deform it by. For a liquid, the force that wants to push it back is proportional not to how much you deform it, but to how fast you deform it.
So that's a force that tries to push back.
So there is in order to keep, so in this example here, suppose I had a liquid here in between and I move this with say some force F, okay? And suppose the rate at which points here move, so again the same thing here, I have suppose this is H and this is D, then D divided by H is a strain. And as I move this, as I keep applying this force, these points go further and further and further up. So that as this increases, I have a strain rate, which is gamma dot. Because D itself depends upon time, so dt by H is gamma dot. Okay? So now what I discover is that the force that I must apply to keep it moving is proportional to the area of the surface. So force is proportional to the area of the surface and is proportional to the rate at which d changes. So proportional to gamma dot. Okay? So the force divided by the area is equal to gamma dot times something here, which is the viscosity. The force divided by the area is the stress, sigma. So for a liquid, this is exactly what the relationship that we wrote down here.
This force is acting in that direction. I mean, the direction of the force is same for the solid and the liquid, right?
So over here, the force that I must apply in order to keep the top layer moving is proportional to the area and proportional to gamma dot. Okay, I must apply a force in order to keep it moving. If I have just one gamma and that gamma doesn't change, suppose I just move it here and I keep it like that, the force required to deform this and hold it in that deformed position is 0 for a liquid. A liquid happily deforms. What it doesn't like is changes in that deformation. So in the time when I take it like this and move it like that, I induce a change in the deformation, and for that it doesn't like it. I have to put in a force in order to do that. But once I make that deformation and hold it straight, I have now deformed my box from something like this to something like this. Now in this state I need no force to hold it like that. It's happy staying like that. Unlike the solid, which would spring back, I have to exert a force on the solid, on the surface of the solid, to prevent it from moving back. For the liquid over here, once I have it in this position, I don't have to exert a force, it doesn't move back. A liquid is happy to change shape. Solids resist shape changes, and the amount of the deformation, the amount of force that I have to apply to sustain a particular deformation increases with that deformation. And the coefficient of proportionality is the elastic constant. On liquids, on the other hand, I have something that where the force, or in this case the stress, is proportional to the rate of change of the deformation, gamma dot. So stress is proportional to the strain rate, and the coefficient is the viscosity. Okay?
So is it equivalent to saying that solids are memory?
No, it's not, because if it was memory, it would remember. So it would remember how much the sequence by which I took it to this point. But suppose I took a solid and moved it first halfway through, then stayed there for some time, then moved it again another halfway through, and I stayed there. That force only depends upon the total deformation. It doesn't depend upon how I created it. If it depended upon how I induced that deformation, then memory would be important. But here the force required to hold it in this position here doesn't depend upon how that state was created for a true solid. Most objects are not exactly solid-like or liquid-like. They're typically what are called viscoelastic. Viscoelastic means they have properties that are both liquid-like and solid-like. And a viscoelastic liquid is something, I guess, silly putty if you've played with it, which is something like something that deforms. It's a sort of common children's toy which behaves like a solid at short times and behaves like a liquid at long times. The other good example is for someone who falls into water. If you have sort of swum and slammed into water and hit your stomach, it can be very painful. That's because water at short times behaves very solid-like, because you're probing the high frequency response. But only the low frequency response of the water is more fluid-like. So it's very easy to move your hands through water. You couldn't move your hands through a solid, but you do this to the water, hit it very hard, that exerts quite a substantial force on your hand. So all materials behave in some combination of solid and liquid. Like these are two extremes of the pure solid where it's forgotten its history, and the pure liquid which is only dependent upon how fast you make the deformation. Okay. Okay, so let's just do a little bit of related mathematics. So all of these materials that show behavior intermediate between solids and liquids, there's a nice word for it. It's called complex fluids. Sometimes they're also called soft matter. In fact, a biophysics course is really often about the soft matter. The fact that biological systems can, for a lot of practical purposes, be described as soft matter. So much of what I told you, for example, about polymers and about membranes and their behavior and how to model them, would also be part of a soft matter course, not just necessarily a biophysics course.
So soft matter means?
Soft matter means matter which is easily deformable. So if you look at what I did here, when I said sigma is g times gamma, the scale of the forces required to create a deformation, this g could be very large. For example, if it's a metal bar, g would be extremely large, which means I would have to have a very large force in order to sustain even a 0.1% deformation. However, materials that are soft tend to have g values that are much smaller. They can be 10 orders of magnitude smaller, which means that relatively small forces are enough to change, to create substantial deformation, which is why these are called soft. And the other reason is that the scale of these forces can also be comparable to the forces that are supplied by thermal fluctuations. So just thermal fluctuations are enough to give you fairly large changes in structure. You can just, for example, soft materials, if you can hold them in the test tube and shake them, that you can have very substantial changes in their configuration and form. Which is the other nice example of soft matter is tomato sauce or ketchup, which if you sort of try to get it to flow, the initial stages of the flow are quite difficult to do, but once you get it to flow, then it flows smoothly. That again has to do with the properties of this material and how the molecular scale properties of this material, but that's also soft again because it flows under forces that are not very large. Okay.
So how do we define the stress equation in those cases for soft matter?
The equations are sort of kind of the same, except that you have to worry now about what was raised and about you have to worry about memory effects. And the reason that many of these soft matter systems behave funnily is that you can have, these are typically not often, but fairly often tend to be made of long molecules. Okay. So if I want to deform a system where these long molecules are all aligned at random, this costs me a certain amount of energy to do. And if I want to deform it where all of them are more or less parallel, this costs me a different amount of energy to do, different scale of forces to do. So exactly how I go from here to here, suppose I'm now trying to shear this. The shearing also has an effect on the molecules. It tends to stretch them out in the direction of the flow. So when I do that, it becomes easier to shear because now all of these molecules are now aligned. So I have to account for the fact that I must remember the configurations of these molecules, how they changed in time, to understand at some later time how easy or difficult it is to deform. So what it really means is that these quantities now become functions of frequency, that I have to worry about the low frequency response and the high frequency response. And the viscosity here, which I wrote as eta, becomes eta of omega, which is frequency dependent response. So this, as in the example of falling into water, so usually if you try and do something very fast, you're sampling the high frequency viscosity. So at different frequencies, they can respond differently. The low frequency response is typically water-like. You're just doing it very slowly. You can move your hands through this water. High frequency is just, as I said, hitting it very hard, causing very short time changes in the configurations of the molecules. And that can have a different number that I would associate with eta. So first of all, many of these quantities become frequency dependent, and you have to worry about history effects. You have to couple the nature of the flow to what the molecules are doing inside. These are the constraints that you have to obey. Okay, so let's imagine a little bit of surface here. Let this have volume nu. Let this be some p here. Let there be a little area element with a normal n hat in this direction. And let me imagine that there is some additional forces here, which might be gravity. So what I am doing here is I have taken my sample and broken it up into what I will call material points. That's the notation I will use. Material point is a set of points here that more or less behave in the same way as I deform it. Okay? Sometimes in the literature on fluids, this is called a fluid particle. In the literature on solids is called a material point. It's just in the spirit of coarse graining or using densities rather than individual atoms. I say let's just take a group of atoms or a group of some small region in the solid where all the molecules behave in approximately the same way and try and write down the forces in the equation of motion for those points. That's the logic that we will try and follow. So let's define a quantity called R, and I'm going to put a hat on top. This hat doesn't mean a unit vector, it's just a sort of my notation for something which I will explain just now. R hat as a function of R and T is the position of a material particle R0, which was at R0 at T equal to 0. So what is this saying? This is saying take your material that you want to study, break it up into these little material particles or little regions that you want to study independently. Look at where that region is moving to in time. If I know where it started, if I know that it started at R0 at time t equal to 0, by telling you where it is now at some later time t, I have told you everything that you need to know. So given all of the R0s for all the material points, at the end of time t, I know how to connect where they started to where they landed up. That's my logic that I will use. The velocity is just, of course, delta of R hat, R0 comma t, divided by delta t, how fast things are moving. With the condition that so this is V at point R at time t. So the condition is that the point R hat R0 comma t is the same as R. Okay? So this may look a little bit complicated, but what it is saying is the velocity of a material particle located at point r at time t is just figuring out which is a material particle that is at that point r, and then asking how fast is that material particle moving. It may look complicated, but in words it's very simple. This just says that the rate at which things are moving at some point r depends upon which material particle it is that has landed up there. So it says the condition of r naught given a start r naught t must equal r, and this is how fast that is changing. So now we are going to consider a small volume enclosing that point. So then the mass is rho times V, where that small volume is called V. So mass, which is rho V times delta 2 r at by delta t squared. This is as a function of r0 comma t. This is F at the total force acting upon that. So this is just Newton's laws. Huh? I know that the mass point is at point r. This is the volume, this is the mass associated with that. So mass times acceleration is the force on the right hand side. Okay? So this is just saying that whatever I have, it must always be consistent with Newton's laws. Now notice that there are two types of forces, or two ways in which two distinct ways in which one can conceptualize the action of the forces on these little volumes. I call it two types of forces, but what I mean by this is that there are forces that are called body forces and forces that are called surface forces, and these are very distinct. What this means is, suppose I take a little region here with a certain number of molecules inside. There are forces that are proportional to the volume. I increase the volume, I increase the force. One force is just simply gravity, because the force of gravity, F gravity, is proportional to the mass times the acceleration due to gravity. But the mass contained in this depends upon how big it is. So it's proportional to the volume that is contained in here. So this mass here would be the density times the volume. This is called a volume force or a body force or a bulk force. Okay? The other part is a surface force. For example, if there are molecules here and here, the molecules outside this volume exert forces on the volume, on the molecules inside this volume. Okay? This acts if you assume that the interactions between molecules are short-ranged, which you probably remember that in most cases you can approximate them to be short-ranged. For example, the van der Waals interaction, which looks like this, has a range of about, say, let us say 2 sigma or something. By the time this is 2 to the power, I think 1 by 6 times sigma, and then you can figure out what this is, all of order sigma. So by the time you get to distances that are a few times sigma, the potential has vanished. So if I thought of particles here and here, this particle here hardly interacts with something here. It doesn't really care about what this particle here is doing. On the other hand, it does care about what this particle here is doing. So these are forces that act at the surface of the volume that I am considering. So these are surface forces. And these are two different types of forces that we need to understand. Um,
in the body of, are there such forces?
In what I will describe, you can put both of them into the common description. This is right now just for you to think about the fact that there is a distinction between forces that act on everything together commonly, uniform. And for example, all of the particles in here are acted uniformly on by the gravitational force. But on the other hand, what these molecules may be doing at this side from a funny curved surface that is being deformed in funny ways, that can differ from this side to this side to this side to this side. So it's not necessary. For example, if suppose these were all, say, charged particles. Now you know that the interaction between charges is a long-range interaction because it's 1 over r. It sort of goes very, very slowly to 0. And even if you're here or here or here, you can still feel that, the effect of that charge far away. So if I have charges floating around on the outside and the inside, then I will need to change this because there is not such a clear distinction between bulk and surface anymore. But for most things that I will consider, where either there is a lot of salt in the system so that it neutralizes the effect of that charge and screens it out, or I just forget about charge altogether and ignore it completely, then all of these interactions generically will tend to be short-ranged. Okay. So now let us describe the effects of these surface forces. Now, as I said in this earlier example where we looked at the rod that was extending, the effect of the force depends upon how the force is acting upon an infinitesimal volume dA with some normal, unit normal n hat. So the force per unit area will have different components in the direction of n hat and components perpendicular to n hat. One way of codifying this is to say that the net force, the alpha component of the force acting on a little element of size dA is proportional to the components of the normal n beta, is proportional to the amount of area dA, and this proportionality constant is something called sigma alpha beta. Now F alpha is sigma alpha beta n beta dA. So this is the alpha-th component of the force acting upon a surface element of area dA with unit normal n hat is sigma alpha beta n beta times dA. So this is the representation of my surface forces.
What was n beta?
N beta are the three components. So nx, ny, nz with the condition that nx squared plus ny squared plus nz squared equal to 1. These are the components of the normal to the surface. So once I tell you that think of an infinitesimal little piece of surface with a normal with components. So I imagine that I have some coordinate system. I think of the surface. There is a normal, and in this coordinate system, the normal is described by nx, ny, and nz. Once I do that, then I can write the force in terms of some quantity called sigma times this n alpha and beta, the three components of the n. Okay. So this, yeah.
It's a vector.
So this force is a vector. This is also a vector. These are all components of a vector. But this quantity here is a tensor. And this is called a stress tensor. Because I want to be able to describe, as I said, the effects of the forces depend upon how they are applied relative to the normal. So the three components of the force must be related to the three components of the normal. But the relationship between these vectors is mediated through a quantity which is actually a tensor. So you must have seen quantities, I don't know if Rahul has discussed this, but for example, if I have some vector, let us say v1 and some vector v2, then v alpha v beta is itself a tensor. Let me call it v tilde alpha and beta. This is now a 3 by 3 object because alpha can go between values 1 to 3, V1, V2, V3. Beta can independently go between values 1, 2, 3. So 3 into 3, this is 9 components. And explicitly here, because alpha and beta are written in this form, we know that it's a symmetric tensor because V tilde alpha beta must be V tilde beta alpha. Okay. So there must be how many? N into n plus 1, 2, 3 into 4 divided by 2, which is 6 independent components of this particular vector, of this particular tensor.
What does the tensor basically use?
So right now you just need to know that it acts as a quantity that mediates these two forces that connect. So this is a vector here, this is a vector here. But these vectors are not directly proportional to each other. So for example, if I said my force F is some constant times some vector D, these are two vectors and what connects them is a constant. It's a scalar constant. So this says the force and the D are always in the same direction. So this is D, then the force is in the same direction. But in general that is not true. Because given an n here, the force can both have components along there and perpendicular to that. So this sigma accounts for that. It is given a normal. I can determine the components of the force by telling you what is sigma alpha beta at every point in space. Okay. So the stress tensor turns out to be very important. This extreme limit where both these point in the same direction is one extreme limit of this. But in general, what defines the relationship between forces and normals here is a stress tensor. So this defines what are the forces that are acting at any point inside this system.
Is it in matrix?
I can write it in a matrix form, but in general, for example, that would mean I would choose a specific basis, for example, a Cartesian basis, write down the components of this, write down the components of this in that basis, and then write down sigma alpha beta in that basis. That can be done. So that is given a specific surface with a normal that I specify, given the forces, I can write down the matrix sigma alpha beta that does it. But right now we just want to be general and say that the forces acting on a surface with normal n hat always have this form. They are proportional to n hat, and the proportionality constant is a tensor. So the total force acting on the surface, F alpha, is obtained by integrating over the whole surface, dA, of sigma alpha beta and beta. So this was just one little surface element dA. If I integrate this over the whole surface, I will find the total force acting upon it. Now notice from here that we must go back to something called Gauss's theorem. And Gauss's theorem basically says that if I have the surface integral of a vector A dot n hat times ds over some closed surface is the same as the integral of del dot A across the volume corresponding enclosed by that surface. So this is a standard theorem in vector analysis. Okay. So notice that the A dot n here appears here because this is just by saying that beta and beta. By the way, I don't know if I mentioned this, but whenever I have two indices appearing together, I sum over them. No? It's very important. I have two indices that are the same. That means I sum over them. So let me I forgot to mention this and I suddenly realized that this is not something that you might be familiar with. But suppose I have a vector V with components V alpha. Okay. The quantity V alpha, V beta has two indices alpha and beta, where alpha runs from 1 to 3 and beta runs from 1 to 3. So there are a total of 9 numbers that I must specify when I tell you about V alpha beta. However, the quantity V alpha, where these two indices appear together, have a special meaning. And this means that this is just V1 plus V2 plus V3. So whenever two indices appear together, I sum over those indices. So what I mean in that context is, suppose I ask what is F1? F1 is sigma 1, 1, N1. I'm going to multiply all of this by dA plus sigma 1, 2 times N2 plus sigma 1, 3 times N3. That's what I mean when I write the alphas and the beta like this. By fixing alpha equal to 1, I sum over the betas here whenever beta appears twice.
Sigma is Sigma is not greater. Summation.
I can, so I could also write this as if I, in terms of summation notation. But this way of just saying that whenever I repeat an index, that is the same as summing over it. That is called Einstein's summation convention. So it comes from a very famous person. So it was Einstein who first noticed that in many of these, the algebra of these indices, they often simplified. If you just made the rule that whenever I have two indices that are the same, I can sum over them. That's really what I mean there, what I've been using all this while. But that's an important thing to remember about notationally, about what it is that we are doing. So here notice that beta appears twice here, so I'm summing over it. And here what I have is, given any one component here, this is actually sigma dot n. It's this quantity. Now that I fix alpha, this is something beta n beta, which is something dot n, given for that particular thing. So therefore I can do the same thing that I did here and change this particular object into the integral over the volume delta sigma alpha beta by delta r beta. Okay? So the alphth component of the force using Gauss's theorem becomes just delta dV, an integral over the volume, not an integral over the surface anymore. Remember, this was initially integral over the surface, this is an integral over the surface. Now it's become an integral over a volume element, times this, the del dot A part is delta by delta R beta of sigma alpha beta. Okay? So having done that, we are now in a position to write the full equation. And the full equation is delta 2 r hat of r0 comma t by delta t squared equal to integral dr over the little volume containing it, delta of sigma alpha beta by delta r beta plus the bulk part, which is rho times the little volume times the force. Let us say the alphth component of the force, in this case this is m times g, so g alpha. So this is now the equation for this little, small little region, this point that I would describe that is moving forward. And remember, all that we have done, don't be fooled by what we've done, don't think it's anything great or anything. All we have done is written Newton's laws. The only twist that we did was, we broke up the force into a surface force and a bulk force. And then we said the surface force we can write in terms of a quantity called sigma alpha beta, which we then wrote out explicitly. In many applications, we will come up situations where there is no external force, so we can just get rid of this altogether. And the other thing, of course, is that even this integral dr, I can write in terms of the density times the rho v factor here comes, and also get rid of that. Not the rho v, but just the v part of it, times delta sigma alpha beta. All I've said is I'm just going to do the integral over the dv and just call it the v, the little volume that I'm considering. Often also, I can really forget about this term too. It's also not particularly important. Yeah.
So the rho v term comes only when that is considered f, right?
When I consider the f, so this term here was the f total I've written as f surface plus f bulk or f volume. This thing I said was rho v, was a mass inside, times the gravity term g. If there is no gravity, or if I can ignore the effects of gravity, I can get rid of this. Huh? If I can say that, look, things are not accelerating in my system, I'm sort of deforming slowly enough that things are slowly moving to the new positions, but they're not accelerating, or I can neglect this acceleration term here. Then I'm essentially left with the result that delta sigma alpha beta by delta r beta must be 0.
I was saying about can you write the second derivative directly equal to rho v times g? The rho v also comes from
This thing directly is this?
no,
This one?
this is the sum of that term plus rho v g, right?
Yes.
But in the left hand side also rho v must be there, right?
Yeah.
Newton's law.
Yeah. So there should be certainly a term in rho here
And a v.
and a v, because that is a mass. You're absolutely right. Sorry. Yeah. Okay. But now I'm going to argue that I'm going to look at systems where the gravity is not very important. These are small samples. I'm not looking at some big sample where the effects of gravity between the top and the bottom are significant. I can get rid of this, provided I don't do things very fast, like change things. I can, where actually there are pieces of matter that are accelerating with respect to other pieces, I can get rid of this. So then the only final constraint that I have is this particular law, which is essentially saying that there is a balance of forces inside my material. Okay, maybe I should just stop here rather than deal with more stuff right now. And if there are questions, just ask me now about any of the stuff that I've covered up till now.
That rho sigma alpha beta by gamma, is that gamma beta?
R beta. Because remember that came from here. A dot n hat ds is integral del dot A. Okay? Del dot is basically delta by delta r alpha acting upon this, where the dot makes sure that I must use the same symbol here and here. So this is just translating this equation into this particular term.
R is like the radius of the, not radius, this, in the Gauss's theorem, we're replacing del R, right?
This one. So this is basically just the gradient operator. So the gradient operator grad is just E beta delta by delta x beta. And here, I should actually put a sum, but I won't put a sum because I know whenever I have beta and beta together, I can always, it's always automatically a summed over. So I'm just taking this and putting it in here. Okay, I can put it as R beta. R1, R2, R3, or delta by delta X, delta by delta Y, delta by delta Z. So the whole point of this so far has been to try and get you to be a little more familiar with a stress tensor, sigma alpha beta. And what are the implications of writing the fact that the forces on the alpha component of the force at any point is just sigma alpha beta, the normal to the surface at that point, times the elemental delta A, the little volume, the area element. So these are the two things that I would like you to remember from this, that when we talk about continuous media and the forces that we want to exert on continuous media, those forces find their expression in quantities called a stress tensor. And a stress tensor codifies what is the nature of the force that is acting to deform your system at every point in space. Okay? Because, very importantly, the action of the force depends upon how it's acting on little elements of the surface. Is it acting perpendicular to those elements? Is it acting parallel to those elements? So I must not even just tell you a force, I must tell you what it is acting on. That is what I supply in terms of the n beta. Okay? So given the normal to the surface, given that it's an infinitesimal surface dA, I can understand what that force is doing by just telling you what is sigma alpha beta. And sigma alpha beta is a different number, is a tensor that is defined at every point in space. Once I tell you what sigma alpha beta is at every point in space, I have told you what are the forces that are being exerted at every point in space. So we should get used to this by trying out some examples. And then the other thing that I would like you to remember, of course, is just that earlier I just used sigma without any indices, because I was looking about very simple deformations. I only deformed one thing at a time. So sigma equal to G times gamma and sigma equal to G times eta times gamma dot are two quantities that you should remember. This is an elastic constant, this is a viscosity. But both of them relate the forces that are required to create either a fixed deformation or a fixed rate of deformation for a liquid. Very importantly, for a true solid, the force that is required to create a deformation is just proportional to the deformation. It doesn't care how fast that happens. For a true liquid, the force required to maintain a certain deformation is 0. But I must require a force to maintain a fixed rate of deformation. So these are important things to remember because they are qualitative statements about how we think about solids, liquids, complex fluids, etc., etc. And we should be prepared to understand simple things as well as more complicated things. Okay?
So how do we measure tensor? How do we know that?
In this case, you measure it by the forces and the normals. So in that simple example here, where I had this, I know that the force is in this particular direction, whereas the normal is the perpendicular direction. So the sigma has only off-diagonal components. So there is a force acting in the x, suppose I call this an x. So if there is n in suppose I call this x and let me call this z. So n beta has only a z component. Okay? So what I need in order to have an x here is that sigma xz should be non-zero. Okay? So that is a force acting along the x direction on a little surface whose normal is in the z direction. That is given by sigma alpha beta. So similarly, by experiments, I can compute all the elements of the sigma alpha beta. Okay? All right, so that's all for today. I'm not here for 1 week, so I think Rahul will probably take my lectures in my absence.